有的我给他发文件做一个装版，然后下一个就都没有了。
Okay, hi everyone. Today we have like two topics mostly that we talk about. The first one will be more about tangent vectors and what is called a vector field, which will be a field where at each point of the space you have a certain vector field, a certain tangent vector. So we talk about these and how to calculate them and like how to represent them in charts. So that will be the first part. And the second part of today's class, or like the second part, we will talk about differential forms, which will be something that like measures in some way how long, for example, or in which direction a tangent vector is pointing. So that's like the rough outline for today. I would like to start with the definition of a vector field. The definition is we have a surface every point on the surface we associate a certain vector. And we want that to have the property that it's really like a tangent vector, not something like, for example, normal to the surface. So we want that x of s equals, is like in a subset of the tangent space. So this one, remember that this one was a certain subspace of R3, and we want that this one is like tangent to the surface. So for example, if you have like the upper semi-sphere, for example, then you can say, you can imagine that at each point you have a certain vector associated. So for example, something like the following would be a tangent vector. So at each point of the of your surface, so also in the front, so to speak. So at each point of the surface, you have a certain vector associated. So say that's the point S, and the vector associated to that point is like x of s, and that's really like a tangent vector at that point. So that's important. So it's really like smoothly varying vectors, and all of them are like tangent to the surface at each point. And it's more custom to write like x of s as like a subscript. So usually I prefer it because otherwise we get too many brackets. So we usually just write like the s as a subscript instead of x of s. So let's look at like a typical example. We can consider like an open subset of R2. And we can consider that one as a parametrized surface. As a parametrized surface with like one chart, which is just the identity. So that's like in a simple way we can consider every open subset of R2 we can just consider as like a surface. And then clearly there are canonical vector fields on D. For example, we could like if that's your open subset of R2, but we can consider at every point we consider the vector that just goes into the x direction. And similarly, we can like of course also consider a different vector field where we just say that all vectors point in the y direction. So these are like in the picture where you have like that's pretty nice. You can like consider at each point you have a vector which points in the x direction, with, say like unit length, and here you have like each pointing to the y direction. And it's actually nice to talk about these vector fields a little bit more because they will be really important later on to study vector fields on some surfaces. So let's look at like how we can define it a little bit more exact. So for every point, x0, y0 in D. So remember that we talked about tangent vectors as certain curves, right? That was like you choose a certain curve that represented that tangent vector and then take like the derivative at 0. So we would like to do the similar thing here. So we consider certain curves. Like taking values in D. So that I is like a small enough interval, say around the 0 point. And we consider that to be just the variation of the point, and then we go a little bit in the x direction. So in this picture, for example, we have, let's say, this one is our starting point, which is x0, y0, and then the curve that starts at that point and then just like goes on and goes on forever in this direction. And you see, like if you have the time small enough, then I'm staying in D for small enough time. So that's why I say here that we have like a small enough interval. Of course, if you go like very long in the x direction, at some point you might exit your D if D is small enough. But for any point, we find like a small enough neighborhood so that this curve makes sense. And what we have is that this curve starts at C of 0, which is just x0 and y0. That's by construction. And as tangent vector at 0, which could be so you take the derivative with respect to here, and this is just 0, 1. Thus we can like say like that this curve represents the tangent vector. For this at the point. So that allows us to think of like a traditional vector. So this one is just like really like a normal vector, right? Like it has entries. But we represent that now as like as a curve. So that means that it's also a tangent vector in our terminology, right? Like the tangent vectors were vectors where we could find a curve such that if you take the 0, like the derivative at 0, then you represent that. So that's like what we do. So in this way, we can represent this vector as a tangent vector. So that's just a bit maybe clearing up like a little bit the confusion about what is the difference between vectors and tangent vectors. So if you consider D to be an open subset of R2, then there really is almost no difference between tangent vectors and vectors. But also, like you see, like the point was like essentially arbitrary. So we can like vary the point and then get like a vector at each point. can do the same construction at every point. So we get a vector field. On D. And this vector field is like just, yeah, like it's a vector field such that if you plug in x and y 0, then it's just a constant vector which points in the 1, 0 direction. And usually we write dx for this vector field. So it's like maybe a little bit confusing, but like dx is like a vector field that points in the x direction on D. So it's like really, like it's just like a notation. So that's really like dx, yeah, like that it's in this pointing in a certain direction. And we will talk about, like, see some examples in the future where we calculate certain things, and then it becomes maybe more clear why that notation is nice. But like, just take it for just like a yeah, notation for this x is just the same thing as denoted by dx. So it's really just like a name, so kind of notation. And of course, we can do the similar trick. We can just like take the vector field that points always in the y direction by just taking, instead of taking t to be written here, we can like write t here instead of right here. And then we get like a second vector field which points in the y direction. And then like, I guess you know already, or you can guess it. And we will denote this one by dy. So it's just like the vector field that points in the y direction is denoted by dy. And you might be tempted to like, yeah, like there are two ways to think about that vector field, right? Like you can either think of that as like it assigns the vector 1, 0 to every point. So like this equation, we have now in this notation that would be dx at some point x0, y0 would be just a tangent vector that goes in x direction. And similarly, dy would be just like a 1 there. And sometimes that's helpful, but usually it's better to just like write everything that you get in terms of dx and dy. So not really like expanding that really in like normal vectors, but kind of considering dx now as like a new name for the vector. So similarly, it's a bit similar to what you do sometimes in linear algebra, where you also have like where you usually write like E1 equals to 1, 0 and E2 0, 1. And of course, usually you can like expand it and like calculate with these terms, but usually it's nicer if you just take them as E1 and E2 and not like plug in the numbers. So it's very similar here that with these vector fields, it's usually better to write dx and dy and like expand things in terms of dx and dy instead of really thinking of that as like vectors. And once we have like a vector or a vector field, it makes sense to talk about like how a function changes in a certain direction. And that will be the next definition, which is the directional derivative. Given a smooth function, defined on the surface, and the tangent vector. Say x at one point of the surface. Then we can associate it with this data. We have the direction now. Derivative of f in the x direction. And this one is denoted by Ts of f. And so that's like the left-hand side is just it's like notation again. And it's denoted by, or defined by, we take ddt of 0 for f of c of t. So that's a real number again. So I have to tell you what the c of t is, and you can already think about that. It's probably related to the tangent vector. Namely, it's like for some curve c in S, the 0, 0 being the point that where we take the tangent vector at, and c dot at 0 should be our tangent vector. Let's have a look at the picture. We have a certain surface. We fix one point here and give ourselves a certain tangent vector at that point. And then we have a function that maps the points on our surface to the real numbers. And what we do is we choose a curve, some curve, that goes in S. And at that point, it looks very similar to x. So it's like the tangent vector of that curve is like a tangent in the same direction as x. So we choose a curve, and then we get a map from the interval into S. And then the right-hand side, the f composed with c of t is just like the map that you get here if you compose them. So you go like in f, or with the curve you go into S, and then you compose it with f to get a real number. And then you take like the change of f, like of this composition as you vary t along t equals to 0. So that defines you the left-hand side, the directional derivative. And it's, it's similar to like the derivative in the sense of that you change, like you have to give like a direction if you want to talk about change of a function on a surface, right? Because there are so many different ways in which you could like change things. You need to give like a direction that you say like, okay, I want to say like, for example, how much the function of like the measuring the height of a mountain changes as I go upwards. That would be, for example, a question. But you need to say like, I want to go upwards. If you just walk around like the mountain at like the same altitude, then the height doesn't change, right? Like, so that's where you need to give like a direction where you say like, okay, I want to know how much my that's like maybe how you can view that as like a small ant that walks up the mountain, and then it says like, okay, how much does the height changes as I walk up the mountain, and then it's like the small ant is like the curve, and then you say like, okay, how much does the function changes as I move along the mountain, and that's like this composition is like the F composed with C is exactly measuring the height of the ant at a given time. And then you're interested in like the first order approximation of that. Okay. So that was like for a given S. So we get like a certain map, right? We can consider now this function there as a function where we let like x vary, and then we get like another map. And it actually turns out to be linear map, which is the Ts of f, which is a tangent vector of the surface and gives us a real number. So this map is like obviously defined, so it's Tf. We have to evaluate it on S. So it's like this expression over there. So we can really consider that as like as a map, and it's like relatively straightforward to check that it's linear. So that's maybe also like why I know some of you might have like got confused by that, but it's like where this notation is coming from T of S. Like it's like two different T's here. Like this one is saying like, give me the tangent space at the point S on the surface. So S is the surface here, and that gives me the space of all tangent vectors at that point. And this one is like saying, okay, I have my function, and I would like to know how the function changes in a certain direction, and that's denoted by Ts of f. So that's like two different T's in this sense. Like it's like one of them is like really the tangent space, and this one is like associated to the function. And similarly, we had last time that the map for a chart was also T of the chart, and that's also more like in the sense of that it's like changing the like how the function changes. And one property is that this definition that we give up here doesn't depend on any chart, right? So we just choose some curve and then we define that by that right-hand side. But it doesn't make any reference to that we need like a chart. So that's like an important observation or remark. Not. And things that are usually defined without respect to a chart, they are called intrinsic. Intrinsic or coordinate. And it's usually quite helpful if you can define certain notions on your surface without a reference to a certain chart, because then it's a bit easier usually to handle that. So that's why we usually want properties that are like dependent not on like some coordinates, and that's we talk about intrinsic properties. So let's have an example. We go back to this example that I just erased, where we look at like an open subset that we just talked about. So again, let the open, and we consider that as a surface. And suppose we have a smooth function defined on that open subset. Then let's have a look what the tangent map at some point. So now I have to give you some vector that is like in this direction, and what I give you is like dx, because that was like the vector field that we just defined. So let's calculate what this side is. So that's so we go back there, up there to the definition. So that's a vector, and this one is the derivative. So we have to calculate d dt at 0 of the function with respect to a curve that represents that vector. But I just gave you these curves. So what we do is that we have x0 plus t and y0. So that's just like using the definition that we had for dx. So now we can calculate that by just like essentially what you learned in your first year probably. So that's like the partial derivative of f into the x direction, and then at the point where t equals to 0, which is just x0 and y0. So what you see is that there's maybe like a bit strange looking notation of like taking the directional derivative of f in the x direction is nothing else than taking the partial derivative of f with respect to x. some people like to write like partial derivatives as like dx on f and then x0, y0. And it's like this kind of notation where that justifies that we would like to write dx because it's like taking the partial derivative of f in respect to x direction is essentially encoded by x acting on f. So that's where this notation is coming from. It's like the dx is just like because it's like somehow if you apply it to a function in the sense of like that you take the directional derivative, then dx is so to speak like the variation in x direction. So that's maybe as a motivation why we write like dx. And of course, similarly, we can like take the partial derivative in the y direction. And an arbitrary vector is just, maybe I write this. So here, directional derivative is a natural generalization of the partial derivative to curved surfaces. So in a plane, it makes sense to talk about like what is like the x direction and the y direction, right? But if I now have like, say for example, that's like something that points in the x direction. But if I now curve that, then it's no longer easy to say like what is now pointing in x direction, right? Like it doesn't even make sense on the surface to say like what is x and y direction. So in that sense, it's like there's no x, like the x would be something that is like going around, like essentially how these arrows point now. So that's like in that way we need like to talk about this directional derivative where we have to give like a direction that we want to talk. And like the partial derivatives, they have like a canonical direction because you say like, okay, I have something that only goes in the x direction or something that only goes in the y direction. But on the surface, you don't have these canonical directions of x and y. That's why everything is a little bit more complicated and you have to insert these tangent vectors there. Okay, so that gives you in some way like the story for open subsets. And now the next question would be if I have like an arbitrary curved surface, how do I relate things that are like on that surface to something that is like on D? Because on D I kind of understand it. On D I know now how to take the directional derivatives, that they are just partial derivatives and stuff like that. So it's like now important to transfer things on the surface back to the open subset, and that's something that is called a chart representation. Or also sometimes called local. So the thing is like, suppose we have some object that lives on the surface. So suppose we have some object. The object is like, it can be a function that lives on S, it can be a tangent vector that lives on S, or we will talk about more complicated objects. But suppose we have something that lives on the surface. Of course, splitting depends on what it means. So we have like some object, and we would like to study that object. And say, for example, natural things would be to say like, okay, if it depends on the points, then one would be like interested in saying how much the object changes if I change the points, for example. So, for example, if I have a function, I would like to say like how much does the function changes as I change in a certain direction, and that's what we talked about, like with the directional derivative. So we want to do calculus, and for that we need to say like need to express object in terms of data on open subsets of R2. So it's very hard to study something that lives directly on S, but like it's way easier to say like we have an open subset D in R2, and we look at like a chart, and then we look at that chart and say like how does like the object that is on here, we kind of like think of that through the lenses of the chart and get an object that essentially lives down here on the open subset. And on that open subset we can like use the canonical tools that we learned like in analysis to study this object that lives actually here. So let's have a look at like first functions, and then in the second part we look at tangent vectors and vector fields. So suppose we have a function which is defined on S, and we have a chart which goes a map from some open subset of R2 into our surface, which we consider as a subset of R3. So that's the data that we have, and we already know that we can like look at the composition. Composition, which I denote by F with respect to the chart. Which is the map that we go first from R2 into D and get at some point in S. And then afterwards, we go from S with the smooth function into R. So we get like the composition is then a smooth function on D with values in R. And this one is called the chart representation of F. So let's have like an example, like a concrete example in mind. Namely, we look at like the sphere. So for example, S we take to be just the standard sphere we have, and we define f of a point x, y, and z, where x, y, and z is some point on the sphere, so the norm of that vector is just 1. And for example, we can consider that to be an easy function. We say like it's just like saying like a c. So it's like the third component. So essentially, what you have is you have the sphere, and the function that gives you the r vector is just taking the projection of the height and just maps that to the real number. So that's a smooth function, like it's some function on S2. And we have seen last time that we can consider a chart which was defined by this expression. By the way, if you don't get confused by I make like sometimes like a tick that doesn't make any things, like it's just in Europe, or at least in Germany, we write like the square root with like a tick afterwards for some reason. So don't get confused why I sometimes have the tick there. So that's a smooth map that we defined last time, which was essentially the projection of that point up here. So it's like just lifting a point and like mapping it to the point at like this on the sphere above it. So that's the chart. And now we look at like the chart composition, which would be a map from x and y. What I have to do is like I first have to plug in phi, which gives you x, y, and then like this expression, and then plug that into f, which gives you the last c component. So this function here is just 1 minus x squared minus y squared, and then taking the square root of that. And this one is a smooth function. Function on D, which was, recall that, was defined to be all the points where x squared plus y squared was strictly smaller than 1. And it's important here that we say like that it's strictly smaller than 1, because if you take the derivative of f, then what you get is like 1 over terms, and then at the points where x squared plus y squared would be 1, this function is not smooth. So like at these points where you have like the equator, so to speak, that's like given by the points equals to 1, would be c equals to 0. At that plane, this function is no longer, like you can't take the derivative of that. But, so that's the chart representation of that simple function. So for functions, it's relatively simple how to get like a chart representation. So now we would like to do the same thing with vector and vector fields. question is now we have a tangent vector at a point on the surface, and we would like to say that we can represent it in some way as certain things that live on the open subset. And last time we have seen that there was this particular map which we defined as a map from R2 into the tangent space with S being the same thing as the image of 0 under phi. And this map we have seen is bijective. And that used essentially that because phi is non-degenerate. And using the same argument, so that's like, the same argument is we get here we take the derivative of where we change the point where we don't have like 0 there, but we you replace, last time we had like this one was like essentially the Jacobian evaluated at 0, and now we take like the Jacobian at an arbitrary point. And that gives us a map that gives us a tangent vector not at like the point where it was 0, but now we